And of course, we are all waiting to see what will happen on March 16th, 2026, when 3i Atlas will come closest to Jupiter. And it comes exactly at the distance where Jupiter's gravity starts dominating relative to the sun's gravity. So the fundamental question is whether it will release any objects that will become satellites of Jupiter. And a natural rock will never do that because in order to deposit objects that will stay bound gravitationally to Jupiter, they need to cancel out the motion of 3i Atlas, which is quite large relative to Jupiter. So if we see anything like it, we have the Juno spacecraft monitoring Jupiter right now, and we will have two other spacecraft reaching Jupiter by 2030, 2031. And these are the European Space Agency's missions that are called the JUICE and the Europa Clipper. So they're on their way there, and if there are any new objects around Jupiter, especially at the Lagrange points, we would notice that.
3i Atlas is releasing a cocktail of chemicals that haven't been exposed to space for billions of years. New data from a NASA spacecraft reveal water vapor, carbon dioxide, and complex organic molecules emerging from this interstellar object compounds known to play key roles in prebiotic chemistry. What makes the discovery more unsettling is what happened next. Instead of fading as expected after its solar encounter, 3i Atlas suddenly brightened, sharply and measurably, indicating that deeply buried material was being activated and expelled. Together, the chemistry and the sudden brightening raise a more unsettling possibility that 3i Atlas may be capable of harboring life in a dormant state, preserved and hidden until the right conditions allow it to awaken. What made the event remarkable was not merely the presence of familiar molecules, but the timing. 3i Atlas had already passed its closest point to the Sun weeks earlier. Standard cometary behavior predicts peak activity near perihelion, when surface ices rapidly heat and sublimate. Instead, this object waited. Its brightening occurred well after solar flyby, suggesting that heat had slowly penetrated deep into its interior, before triggering a delayed release of volatiles. This behavior implies insulation, structure, and depth characteristics that challenge simple models of loosely bound interstellar ice. Infrared spectroscopy revealed water vapor unmistakably, along with carbon dioxide, a compound central to planetary atmospheres and carbon chemistry. More striking was the detection of organic molecules such as methanol and methane, alongside cyanide-bearing species. These compounds are not biological signatures on their own, but they occupy a critical position in prebiotic chemistry. Cyanides, in particular, are known to participate in pathways that can produce amino acids and nucleobases under the right conditions. Their presence in an object formed beyond the solar system suggests that the chemical precursors of life are not rare accidents of Earth, but widespread products of stellar and planetary formation. The brightening itself was not uniform. Alongside gas emission, SPARE-X detected evidence of large dust grains and rocky debris being ejected into the coma. These were not micron-sized particles easily lofted by gentle outgassing. Their size implies energetic internal pressure or focused jets capable of lifting solid material. This again points away from a fragile, porous snowball and toward a mechanically coherent body with internal reservoirs capable of storing and releasing energy over time. From a purely observational standpoint, 3i Atlas represents a breakthrough. It is only the third confirmed interstellar object ever observed, yet it is the first to deliver such a chemically rich and dynamically complex display under direct infrared scrutiny. Unlike earlier visitors, which sparked debates over shape, reflectivity, or non-gravitational acceleration, this object is offering something more tangible, chemistry that can be measured, quantified, and compared directly to known processes in planetary systems. These findings inevitably drew broader interpretation. Among those exploring the implications was Avi Loeb, who framed the observations within a larger astrobiological context. Rather than treating 3i Atlas as an isolated curiosity, he emphasized its role as a messenger from another stellar environment. If an object like this can preserve water and complex organics while traveling for millions or billions of years through interstellar space, then the raw materials for life may be routinely exchanged between star systems. Loeb argued that interstellar objects could act as natural transport mechanisms for prebiotic chemistry. Shielded beneath insulating layers, complex molecules could survive radiation exposure and extreme temperature swings. When such objects encounter stars like the Sun, delayed heating could expose these materials, as appears to have happened with 3i Atlas. This does not require biology to be present, only chemistry, and chemistry, the observations show, is undeniably there. He also noted that the delayed activation strengthens the case for preservation. Material released long after perihelion is less likely to be surface contamination or recently altered matter. Instead, it may represent ancient chemistry frozen into the object since its formation. In that sense, 3I Atlas functions as a time capsule, carrying information about the chemical conditions of another planetary system long before Earth even formed. As compelling as the chemistry is, it is only part of the story. When astronomers began to analyze the object's trajectory and physical behavior, a growing list of anomalies emerged. Features that, taken individually, might be dismissed as statistical flukes or observational limitations, but together form an unusual pattern. 3I Atlas follows a retrograde orbit that is closely aligned with the plane of the solar system, a configuration that immediately stood out to orbital dynamicists. Interstellar objects are expected to approach from essentially random directions, reflecting the turbulent motions of stars and debris within the Milky Way. While alignment with the ecliptic is not forbidden by physics, the probability of such a coincidence is low. The geometry becomes even more striking when combined with the timing of the object's encounters with major planets. Rather than a chaotic sequence of gravitational flybys, the trajectory appears unusually orderly, with planetary encounters spaced in a way that seems structured rather than accidental. Although gravitational dynamics can produce rare alignments, the combination of retrograde motion, ecliptic alignment, and encounter timing places 3I Atlas well outside the expectations for a typical interstellar visitor. The object also displayed a pronounced sunward jet, forming a long and narrow anti-tail that extended in a direction opposite to the one usually seen in cometary dust tails. Anti-tails are a recognized phenomenon, often arising from geometric effects when Earth passes through the plane of a comet's orbit. However, such features are typically short-lived and diffuse, dispersing as viewing geometry changes. In the case of 3I Atlas, the anti-tail remains sharply defined and persistently collimated over an extended period. This level of coherence suggests a focused and sustained outflow, rather than the broad isotropic sublimation expected from irregular rotating surfaces. Explaining such behavior requires invoking either highly localized active regions, unusual internal channeling of material, or mechanisms not commonly observed in known cometary nuclei. High-resolution imaging revealed an even stranger feature, a system of 3 distinct jets separated by roughly 120 degrees, forming a geometric symmetry that is rarely observed in natural comets. Most cometary jets arise from irregular surface topography fractures, cliffs, or randomly distributed ice pockets that activate unevenly as the nucleus rotates. The result is usually chaotic, asymmetrical outgassing that evolves rapidly over time. In contrast, the jets observed from 3I Atlas appeared unusually stable and evenly spaced, suggesting a degree of internal order. Such symmetry implies either a highly unusual internal structure or a remarkably specific distribution of active regions beneath the surface, both of which challenge standard assumptions about how small icy bodies form and evolve. The orientation of the object's rotation axis added another layer of improbability. Observations indicated that the spin axis was aligned close to the direction of the Sun, a configuration that allows jets to remain continuously illuminated and active over extended periods. While this alignment maximizes sustained outgassing, it is statistically uncommon for a randomly oriented interstellar object. Maintaining such alignment over time would require either a precise coincidence of rotational state and external torques or a stabilizing influence acting on the nucleus. For typical comets, solar heating tends to alter spin states unpredictably, making long-term alignment difficult to sustain without fragmentation or rotational disruption. Dust analysis further complicated the picture. The grains released by 3I Atlas were significantly larger and heavier than those typically observed in cometary comae, indicating that the nucleus possesses a high degree of internal cohesion. Many known comets are loosely bound aggregates, often described as rubble piles, that shed fine dust easily and can fracture under modest internal stress. In contrast, this object appeared mechanically robust, capable of channeling energetic outflows strong enough to loft large particles without breaking apart. Such structural integrity suggests a formation history involving stronger bonding, compaction, or thermal processing than is common among solar system comets. Color measurements provided another clue that 3I Atlas does not fit neatly into existing categories. The object reflected sunlight with a bluer spectral slope than most known comets, which tend to appear redder due to complex organic coatings or fine dust mantles. A bluer appearance points to different surface or dust scattering properties, potentially linked to larger grain sizes, cleaner ice, or an unusual mix of materials. These optical characteristics hint at compositional or textural differences that may reflect a formation environment unlike that of bodies formed around the Sun. Spectroscopic ratios also deviated from established norms. In particular, the relative abundance of metallic elements such as nickel compared with volatile compounds like cyanide did not align with patterns seen in well-studied comets. Such ratios are sensitive indicators of formation temperature, radiation exposure, and chemical processing. The anomalies observed suggest that 3I Atlas originated in a stellar environment with different chemical conditions or thermal histories than those present in the early solar system. Rather than being a familiar type of comet displaced from another star, it may represent a class of interstellar objects shaped by processes that astronomers are only beginning to recognize. The evolution of the object's brightness proved particularly challenging for standard comet models. Instead of reaching maximum luminosity near perihelion where solar heating is strongest and then fading in a predictable decline, 3I Atlas brightened significantly later and followed an uneven trajectory of increase and decay. This asymmetric behavior suggests that surface sublimation alone cannot account for the observed activity. To reconcile the data, models must invoke deeper internal processes, such as layered insulation that delays heat penetration or subsurface cavities capable of storing volatiles under pressure. These mechanisms imply a complex internal architecture rather than a simple, homogeneous icy body. Even the object's arrival direction attracted attention. Its incoming trajectory places it near the region of the sky associated with the historic WOW signal, a powerful and still unexplained radio burst detected in 1977 during a search for extraterrestrial intelligence. While no causal connection is suggested and the overlap may be coincidental, the alignment is statistically notable. In the context of an object already exhibiting multiple rare properties, the spatial coincidence adds another low-probability element to an already unusual profile, reinforcing the sense that 3I Atlas occupies an edge case in interstellar object studies. None of these anomalies, taken in isolation, constitutes evidence of anything beyond natural astrophysical processes. Each can be explained, at least in principle, through combinations of geometry, composition, thermal history, and chance. The scientific unease emerges not from any single feature, but from their convergence. When trajectory, rotation state, jet symmetry, chemical composition, dust properties, and brightness evolution are considered together, 3I Atlas begins to diverge sharply from known comet populations. It does not comfortably fit existing categories, instead presenting itself as an outlier that may require new models, broader assumptions, or entirely new classes of interstellar bodies to fully explain. This does not mean abandoning natural explanations. On the contrary, it means expanding them. Interstellar objects may not resemble the comets we know because they did not form under the same conditions. They may originate from denser disks, different radiation environments, or planetary systems with architectures unlike our own. 3I Atlas could represent a class of objects that has simply never been observed before. What is undeniable is that the December 2025 observations changed the conversation. 3I Atlas a longer just an interstellar passerby. It is a chemically active, structurally complex body carrying information from beyond the Sun's influence. Its brightening was not a curiosity, but a signal one that revealed water, organics, and internal dynamics at a level never before seen in an interstellar object. As future telescopes and missions come online, objects like 3I Atlas will no longer be rare surprises but anticipated targets. Each will bring with it a piece of the galaxy's chemical history. Some may be mundane. Others may challenge assumptions as profoundly as this one has. For now, 3I Atlas stands as a reminder that the boundary between stars is not empty, and that the ingredients for life do not belong to any single world.